All right, let's jump right in. Today, we're going to tackle a problem that has, let's just say, humbled a few physics students over the years. And there's a good reason it's a classic, right? It's not just about plugging in numbers. It's about really thinking like a physicist.
So where does this challenge come from? Well, it's from the one and only I.E. Irodov's Problems in General Physics. If you know, you know. This book is famous, or maybe infamous, for problems that really force you to go beyond just memorizing formulas. They make you understand the concepts. And let me tell you, problem 1.44 is a perfect example of this. Okay, so let's get into the nitty-gritty. What's the setup? We've got a wheel, and it's spinning up. It's accelerating. We're given this neat little equation for its rotation angle, phi equals a times t squared. We know what a is. Our mission is to find the total acceleration of a single point right on the edge of that wheel at a very specific moment, t equals 2.5 seconds. And they throw us a bone. They give us the linear speed of that point at that exact same time.
So before we even touch a calculator, we need a plan. And the key here is understanding what total acceleration even means for something spinning in a circle. It's not as simple as you might think. It's actually a combination of a couple of different things working together.
The magic words here are non-uniform circular motion. See, our wheel isn't just cruising along at a steady speed. Nope, it's speeding up. And because it's speeding up and turning, we've got to deal with two separate parts, two components of its acceleration. Let's unpack that, because it's super important. First, you have the tangential acceleration. Think of this as the gas pedal. It's what's making the point on the rim go faster and faster. Then you have the normal acceleration. You might also know it as centripetal. This is the one that's constantly yanking the point towards the center, forcing it to turn and stay in that circular path. So one changes the speed, the other changes the direction. Make sense, right? And boom, that gives us our game plan. These two accelerations, tangential and normal, are always at right angles to each other. And what do we do with two things at a right angle? You guessed it, good old Pythagorean theorem. So our job is simple, really. Find the tangential part, find the normal part, and then combine them. Okay, let's do it. First up, the tangential acceleration. This is all about that speeding up part of the motion. We're going to start with the one thing they gave us, that equation for the angle, phi equals at squared. Now don't worry, we just need a little bit of calculus here. If we take the derivative of the angle with respect to time, we get the angular velocity, omega. And if we do it one more time, take the derivative of omega, we get the angular acceleration, which we call beta. And look at that, it simplifies down to just 2a. Nice and clean. Now notice something really cool here. The angular acceleration beta is just 2a. There's no t in that formula, which means it's constant. The wheel is speeding up its rotation at a steady rate. So we just plug in the value for a that they gave us, and we find that beta is 0.40 radians per second squared. That's our angular acceleration. Okay, but that's angular acceleration. How do we get the linear acceleration of that point on the rim? It's simple. You just multiply by the radius, r. Think about it. If you have a huge wheel, a point on the edge has to cover a lot more ground to keep up, so its linear acceleration is going to be bigger. Makes total sense. And here it is, the classic Irodov twist. We have our formula, W tangential equals r times beta, but wait a second. We don't know r. The problem never told us the radius of the wheel. So are we stuck? What do we do now? Nope, we're not stuck. This is where we have to be clever. This is the real physics thinking. We can actually use the other pieces of information they gave us to work backward and figure out that radius. So here's the plan. Remember how we found the equation for angular velocity, omega? And remember how the problem gave us the linear velocity, v, at that exact same time of 2.5 seconds? Well, there's a beautiful, simple relationship connecting them. V equals r times omega. We know v, we can calculate omega, so we can solve for r. Okay, step one of this mini quest, find omega at t equals 2.5 seconds. We use our formula, omega equals 2at. We plug in the numbers, and we get a nice round 1.0 radian per second. Easy enough? And now for the big reveal. We rearrange our little formula to r equals v divided by omega. We plug in the v they gave us and the omega we just found, and voila, the radius is 0.65 meters. See, it was hiding in the problem the whole time. Now we're back in business. Awesome. We found the missing piece. Now we have everything we need to knock this out. Let's get back to our main goal, calculating those two acceleration components.
So let's circle back to that tangential acceleration. We've got the formula tangential equals r times beta. We now know r is 0.65 meters, and we already figured out beta is 0.40. Multiply those together, and we get 0.26 meters per second squared. That's one component down.
All right, next up is the normal acceleration. The formula for that is v squared divided by r. We were given v, and we just thought r. Let's plug them in, and that gives us a normal acceleration of 0.65 meters per second squared. Component number 2, done. Okay, people, this is it. We've done all the heavy lifting, we found the tangential part, we found the normal part. Now we just have to put them together to get the grand finale, the total acceleration. And how do we do that? Back to our roadmap, that trusty Pythagorean theorem. So, we just plug our two components into the formula. We take 0.26 squared plus 0.65 squared, add them up, and then all that's left is to take the square root of the result. This is going to give us the overall magnitude of that total acceleration. And the number we get is 0.70 meters per second squared. There it is. That is our final answer. After all that work, that's the total acceleration of that point on the wheel. Pretty cool, right? So let's just recap what we learned here, because it's super useful. First, if something is spinning and speeding up or slowing down, you've always got to think about two kinds of acceleration, the one that changes speed and the one that changes direction. Second, since they're perpendicular, the Pythagorean theorem is your best friend for finding the total. And maybe most importantly, this problem shows that sometimes you have to be a detective. You got to use all the clues the problem gives you to find missing info, like that radius. And I'll leave you with a little something to chew on. We did this entire problem for a wheel that was speeding up. But what if it was slowing down? What would change? How would that affect the tangential acceleration, and what would that do to the total acceleration? Give that some thought. Thanks for diving into this one with me.